Can you see sound? Well, actually you can, and today we're going to do it using fire. To do this, my brother and I are going to be constructing a Rubens tube, which should look something like this. The Rubens tube was first described by Heinrich Rubens and Otto Krieger Menzel back in 1905 as a teaching apparatus to demonstrate acoustic effects. Basically, it's a long hollow tube that can be filled with a flammable gas. Holes in the top of the tube allow for the burning of this gas. Essentially, it's a long barbecue gas burner. But before we get to the build, we need to look at the physics of how it works. And to do that, we need to look at some acoustics and a bit about standing waves. Sound travels by compressing and decompressing particles. If we have a gas-filled tube, that means when we pass sound waves into it, there'll be areas that end up with more gas than others. For the Rubens tube, that means when we pass sound waves into it, the areas that end up with more gas will push more flammable materials out of the holes in the top, creating localized bigger flames. The opposite goes for the areas with less gas. So, if we take the height of the flames along the tube, we can actually see what the sound wave looks like. A standing wave, or stationary wave, is the combination of two waves traveling in opposite directions. The result, as the name suggests, is the appearance of a wave that does not change position. The same physics is also kind of responsible for this. I guess fire is the safer option today. Here, we're going to keep it simple and work in one dimension. If we manage to construct our tube correctly, then with the right frequency, we should be able to find a point where the sound wave looks like it's standing still. So, let's give it a shot. Welcome to our garage, and today we're going to be turning this pipe into a Rubens tube. The tube itself was made from a galvanized steel downpipe. After choosing a length of 1.6 meters, we cut it to size, then marked out where the holes would go using masking tape. A total of 70 holes were spaced 2 centimeters apart, with a 10 centimeter margin at either end so that the caps that we would eventually put there wouldn't overheat. Then, to seal one end, we used a tin of beetroots, minus the beetroots, which was attached using copious amounts of silicone. The other end was sealed with a flexible membrane made from a glove and held on with rubber bands so that the sound could be passed into the tube. Though we did go through a few different types of glove before eventually using a robust pink kitchen glove. Whilst this was going on, we also drilled a single large hole into the side of the tube to act as an inlet valve for the gas. To this hole, a standard gas attachment part was pushed in. Unfortunately, I had drilled the hole a little bit too big, so I had to use a soldering iron to hold it in place. Then we applied even more copious amounts of silicone to ensure an airtight seal. The final step was to build a stand that would hold our fire pipe. So we found 2 large wooden boards to make an A-frame out of. Then hinges, screws and 2 small bike racks later, we had a state-of-the-art holding thingy ready for testing. Well, we set out with 3 main goals in our aim. To see if the tube itself worked, to see if we could get a standing wave, and to play some cool music. That isn't under copyright. My hypothesis was that it would work, because, well, it was constructed like many other successful Rubens tubes. How well it would work, I was a little apprehensive. So, we hooked up the gas bottle and let the flames begin. And off to a great start, or at least it lit up and gave us flames of roughly equal height. which is an important first step. We then put the speaker to the glove membrane and played some notes. After some disappointing moments of testing different frequencies, we did it! It worked! It lived! We got a standing wave! But that wasn't the best one. At 408 Hz, we got this. Let's just play that and see what happens. Magnificent. And now for the really fun part. By counting the number of wavelengths in the standing wave, I could figure out that this was the 13th mode. If you don't fully understand what different modes are, don't worry, it just allows me to do the following. Since we know the frequency, the length of the pipe, and now the mode, with a bit of maths, we could calculate the speed of sound through the butane gas in the pipe as 201 meters per second. After searching the literature, I found a value for the speed of sound in butane as 194 meters per second at 300 degrees Kelvin or 26.85 degrees Celsius, and what I assume is atmospheric pressure. Since the speed of sound will increase with temperature and the tube will probably be a bit warm, after all we got a fire right next to it, then I think this is within a safe margin to call a success. Now, what you've all been waiting for, some more music visualized with fire. And for that, I'm going to leave you with my outro music. Remember, I'm almost a doctor, and until next time, be like a proton. Stay positive.